Hi, good evening. I'm Mark Brooker from Amazon Web Services. I'm a principal engineer with the IoT and serverless organizations. And today's talk is a bit of a crossover of those two, of serverless, which is or Lambda, which is a key part of our serverless product, and IoT with Greengrass. Thank you for joining me. Instead of going to the pub crawl, I'm going to try and keep this light and interesting and entertaining for all of you, although we will be diving deep into some code and some of the technology behind Greengrass over the course of the next hour. What I'm trying to convey over the course of this talk is that with Greengrass, we've introduced an exciting new thing, which is extending the Lambda programming model outside the data center into essentially everywhere. By putting Greengrass onto IoT devices, we can take Lambda into your home, into factories, into mines, into warehouses and fulfillment centers, and onto farms, and into all of these places that it just wasn't possible before. And for those of you who heard John Turo's talk today, would have heard about the 3 laws of Greengrass that made us think about this. And this talk is a very different look at that. This talk is a deep dive into some of the code and some of the architecture that you can build with Greengrass, and build, most importantly to me, across both Greengrass and the cloud. So it's not just about programming on devices. It's not just about programming in the cloud. It's about having a single model that allows you to program both devices and the cloud. And once you've learned one, you can apply that in both places. And I think that's extremely powerful. So over the next, however long this takes, probably 40 minutes or so, we're going to design a single architecture spanning devices in the cloud. I'm going to work through a fairly artificial example, but a fairly real-world example, and show how you would build a real system out of Greengrass. We're going to look at some of the code for Lambda Functions, both in the cloud and on AWS Greengrass. And I'm going to try and highlight some of the important bits of the API and important bits of the capability that we've built into Greengrass. We're going to work through the example architecture and why we made these architectural decisions. And I'm going to show a lot of Python code. And I've chosen Python on both sides for this example, although the cloud parts you can definitely build equivalently in Node or in Java. So part 1, let's take a look at what we're building. So my world has 2 places. It has a building on the left-hand side, and this building in this example is probably a factory or a warehouse. And inside this factory or warehouse, there's a fleet of sensors. And here I've got 12 sensors, but it could be hundreds or even thousands of sensors. And these sensors are the Greengrass devices. These are small, low-powered, classical IoT devices. They're going to run the AWS SDK and interface with Greengrass. And also in the same location is a Greengrass core. And this is a slightly more capable piece of hardware, something of the Raspberry Pi size, or potentially bigger. And again, as John highlighted in his talk, we've set a minimum size for Greengrass core, but we don't believe there's a maximum size. We think that can scale up to any piece of hardware you want to run it on. And then on the other side of the architecture, we have the AWS cloud. And here I'm going to combine 4 different AWS products, and I'll add a few more as we go along. I'm going to use AWS IoT as a way of getting the messages from my Greengrass core into the cloud. Then when those messages arrive, I'm going to trigger a AWS Lambda function. So this is the cloud side Lambda I talked about in the introduction of the talk. And then I'm going to use SNS. So let me talk a little bit about what this example is. The example I want to build here is a notification for a human when something interesting happens with this fleet of sensors. In this case, I'm going to highlight what Greengrass can do by saying that some of these sensors are temperature sensors. They're smart thermometers. And some of these temperatures are humidity sensors. And what I want to alarm on and what I want to tell a human about is when the combination of temperature and humidity cross certain thresholds at the same time. And those of you who have run big facilities will know that sometimes when temperature drops and humidity rises, condensation can form, and that can be bad for product, it can be bad for electronics, it can be bad for all sorts of reasons. So in this example, I'm going to go through building something that will tell a human via SNS, so that could go to mobile push, it could go to SMS, it could go to email, tell a human when these thresholds are crossed. So we're going to build the first part of this on the cloud side, and this is in Lambda. So first, what is AWS Lambda? And this is straight off the detail page at aws.amazon.com. AWS Lambda allows you to run code without provisioning or managing servers. You just upload your codes, you just write your code either in the console, in your favorite editor, and Lambda takes care of everything required to run and scale your code and run it with high availability. So you don't have to worry about handling failures, you don't have to worry about HA and so on. And for those who are interested in Lambda, there's a full day of serverless focused talks tomorrow. You can set up your code automatically to trigger from other AWS services, or you can call it directly from a web or mobile app. And in this case, in this example, I'm triggering from another AWS service, and in particular, I'm triggering from AWS IoT. So I'm going to get my Greengrass core, and I'll show you how to do this later in the talk, get my Greengrass core to send an MQTT message to AWS IoT. And AWS IoT is going to trigger the Lambda function I'm about to write. And it's going to implement this business logic about, should I tell a human? And so let's dive in and look at the code. So specifically, we're looking at the cloud side code, and this is the bit of the architecture in the orange box. So the first thing that we're going to do in this code is unpack that MQTT message. And here I've just chosen JSON, but this is really an arbitrary choice, and you can use whatever wire format you want and pack that up into this message. So nothing particularly interesting here, just showing that what the Greengrass core is posting up into this cloud is a message with the building ID, obviously, because I want to support multiple buildings in my architecture. An event, which is or the maximum temperature, and this is an aggregation. This will be an aggregation of the maximum temperature across my whole fleet of temperature sensors, and the maximum humidity, which is also an aggregation across this whole fleet of temperature sensors. But more on that later. Before I go on, I was reminded by a conversation with a customer just yesterday about a Lambda performance tip that I wanted to make sure I shared with everybody. And one of the cool things about improving Lambda performance is that when you improve your Lambda performance, your functions run faster, and because you're paying at a superfine grain, you're paying per 100 milliseconds, you pay less, and that's great. So improving your performance also reduces your bill, which is very exciting. So Lambda, one of the things that people probably don't know about Lambda or don't notice about Lambda immediately is there is an aspect of container lifecycle. And what that means is the first time you invoke a Lambda function, it's going to start up a container. We're going to start up a container in the background. It's going to load your code, and it's going to execute the sort of static portion of your code. And then every time that function gets triggered, the handler function inside your code will be called. So you can break your code down in a Lambda function into two parts. There's the static portion, which runs once per container start. So there'll be once the first time you call it, or as we scale your fleet up. And then the code that runs on every invoke. And when you know this, there's some very interesting optimizations you can do. And the most obvious optimization, and often one of the most powerful, is to create things like your AWS clients up there in that static portion. And that allows them to reuse connections and reuse the SSL handshake they've done and so on across multiple invocations of your Lambda function. It also reduces the amount of garbage, it reduces the amount of time required to start up those SDKs and so on. So if you're doing any kind of initialization, you'll want to do that once up in this kind of top section of your code. You do want to be careful though, because Lambda can terminate that container at any time, and obviously when you're scaling down, you're going to stop seeing some containers. So you don't want to put code that needs to be durable there, or data that needs to be durable there. You want to put in clients, you want to put in soft state, you want to put in pre-calculated things that can reduce the runtime of each invocation of your function. So now we've talked about that. Let's move on to loading configuration and history from DynamoDB. And here I'm using DynamoDB to store the history of these messages I'm getting. So when I get every message, I'm going to load the previous value of the message, and you'll see why in a second, from DynamoDB. And then I'm going to save the new values into DynamoDB. I've also got some logic here to handle the case that there are no existing values in DynamoDB, so the first time this system starts up. And here I'm just using the very standard AWS SDK. I'm calling the DynamoDB get item API to load the data for this building ID. So this is the building ID that was passed in that MQTT message. And if the item's there, I'm going to use the values from it, and if it's not, I'm going to use the default values. And loading from DynamoDB lets us apply some latching logic. And this latching logic is going to make sure that when we tell a human, hey, your building has crossed this threshold, we're only going to do that once. We're not going to do that again when the next message comes in, and again when the next message comes in. We want to do that once. And in a real-world example, you would probably implement something fancier than this, probably some hysteresis. So if it's wobbling around that line, you don't get multiple messages. But this is the simplest form of deduplicating based on DynamoDB. And the other thing here in the first function, you can see that we use some configuration, and that configuration is a little map that you could put into your Lambda code, or you could put it in DynamoDB, or you could put it in another database and use that as a configuration store. And a little bit more, and I'll talk a little bit more on why that's so powerful in the IoT space later. So here we call that function to load the previous values from DynamoDB. We load the configuration from DynamoDB, so this kind of per building configuration. This allows a human to set those knobs. And then we say, well, if we should alarm on these values, and we didn't choose to alarm on the previous values, then we're going to send the SNS notification. So this is the logic that's going to send just once. And then we send the notification with SNS. And again, just make a nice JSON blob and pass this into SNS. And on the SNS side, we've configured what's going to happen to things published to this topic. And that could be sent to any or all of the syncs that SNS supports. So one of the things that's really, really powerful about building these kinds of architectures in the cloud is its extensibility. Once we've got the stream of messages coming in from the IoT devices, we can very easily do multiple things from them. For example, we're already writing, updating each message or updating DynamoDB as each message comes in. We could enable an update stream on that DynamoDB table, hook a Lambda onto that update stream, and do further aggregation, or load the data into something like Amazon Redshift for future analysis. So this is showing just how powerful it is when you start getting this data flowing up into the cloud. You can very easily configure things to send that data to multiple places and get value out of it in multiple ways. And that's why we would choose to architect something with some of it local and some of it in the cloud. We would choose some of it local for some reasons I'll talk about as I get into the local side of this. But we'll put some of it in the cloud because it gives us a lot more options of looking over a broader view, looking over multiple buildings or multiple systems. It gives us the option of keeping a lot of history. It gives us a lot option of using the powerful analytics capabilities and database and storage capabilities in the cloud to deal with that history. So let's talk about the local side of this. And here I'm going to call this local filtering, but really this is a few things. What we're going to build on the Greengrass side is we're going to build a rate reducer. And we're going to build that rate reducer because in this example, and that came out of my head, each of these sensors sends its data every second. Right? And if I have 1,000 sensors in the building, that's 1,000 messages a second of, hey, it's 30 degrees, hey, it's 30 degrees, hey, it's 30 degrees. And each of those messages has fairly low value. So if this building has unreliable connectivity or expensive connectivity, you don't want to be sending the 1,000 TPS of particularly uninteresting messages up into the cloud. You also want to perform local, so what you want to do in Greengrass is to get those messages and filter those messages down. And in this case, what we're going to do is we're going to get the maximum temperature seen across the whole building, and we're going to get the maximum humidity seen across the whole building. And we're going to post that up into the cloud once a minute. So you've got this 1,000 TPS, so 60,000 messages a minute, coming in from this fleet of sensors to the Greengrass core. And the software, the Lambda function that we're about to write for the Greengrass core, is going to take that and it's going to cut it all the way down. It's going to aggregate it all the way down. It's going to filter it to get just one message a minute up into the cloud. So you can just imagine over an expensive radio link, for example, this could be a huge cost improvement. It's also an availability thing. If this facility drops off the internet, you want the aggregation and filtering to continue. Yeah, so we have these messages coming into the core, and we're about to build a Lambda function to filter these. And this is the Lambda Anywhere magic. The function we're about to write is just going to be normal Python code. It's just going to be the same kind of normal Python code that you would build for Lambda in the cloud, but you're going to run this on a device. And Greengrass is going to allow you to build and manage and deploy that onto a device, onto the device running this Greengrass core software. So I'm going to make heavy use of shadows in this example and talk a little bit about the 3 different roles that device shadows play. If you look at IoT device shadows in AWS IoT, they play the role of being a copy of the state of a device. They allow a device to synchronize its current state to the state in the cloud, to handle these cases of intermittent connectivity and so on. With Greengrass, we've kept the one shadow mechanism, but we've added 2 new ways to use shadows, or 2 new powerful things to do with shadows. One of those powerful things to do with shadows is to have local-only shadows that you can use as a local state stash on that Greengrass core. It's like a tiny mini local database in this document to keep local state, and that's what we're going to use to keep the local state as we do this aggregation and filtering locally. And then I'm going to talk about another role of shadows a little bit later, which is synchronizing shadows between the cloud and the core. And there's some super powerful things you can do with synchronized shadows. Obviously data transfer is one of them, but there are also things like pushing down configuration and pushing down changes and values to these devices, which can give you a huge amount of control. And in a lot of IoT cases, you're going to be doing a long testing cycle for a piece of software, a long qualification cycle. And while Greengrass aims to make it as easy as possible and as fast as possible to deploy, often there are constraints that make it difficult to make code changes. So having the ability to do dynamic configuration using synced shadows is an extremely powerful thing. So let's look at this sort of loading and parsing a shadow. And what I want to highlight here is Greengrass comes with a built-in client for these local shadow and messaging capabilities. So you're just going to write this code that says, IoT client.getThingShadow. and it's going to load the shadow for the thing. And in this case, the thing that this shadow corresponds to is the Greengrass core itself. So we're going to load this shadow, and then we're going to parse the JSON, and then we're going to, to get a version out of that shadow, because this is good practice. When you write some state down, you want to version that state to allow you to do optimistic concurrency control. And there's another role of shadows. There's a fourth role of shadows, is it allows you to do OCC type patterns, so optimistic locking patterns with lambdas on the device. So when multiple concurrent lambdas are running, you can just imagine that two messages of these come in from these sensors at the same moment. Multiple concurrent lambdas are going to start up, and you don't want them to tread over each other and do something illegal. So we're going to use the version in the shadow to make sure that we're doing the right thing in that concurrent case. And then, again, we are going to handle the case where there is no shadow. So this is the bootstrapping case. Just like we saw with local, this is the bootstrapping case that says, well, there is no shadow. So I'm just going to start off with some default state. And this default state is, well, we haven't written down any aggregation state. So the architecture I'm building here, the sort of little mini in this function architecture, is I have the MQTT topic, which all the sensors are talking to. I have my Lambda function, and then I'm going to use a shadow to record the high water mark. So that's these maximums that I'm aggregating. Aggregating the maximum temperature and the maximum humidity that I've seen from that whole fleet of sensors. I'm going to use another shadow to record the last time I posted to the cloud. And this allows me to do this kind of once a minute thing with messages coming in every second. I want to say, I'm getting 1,000 messages a second. Oh, I haven't posted in a minute. I'm going to post that data now. And Greengrass will provide you with two ways to do this. One is the pattern that I'm using here, where I'm using the shadow to say, how long ago has it been since I last posted this message up to the cloud? Oh, it's been a minute. I must do it now. It's also going to provide a event or cron type functionality where you can say, run this Lambda once a minute. So that's an alternative architecture, which I haven't chosen here, because I like to keep this to one function. And then I'm going to use an MQTT topic in the cloud to send the message from my Greengrass core to the cloud, which is then going to go to that Lambda function that we saw earlier. So the next thing I want to show you is updating a shadow, and here's where I'm going to implement this optimistic concurrency control pattern. So I'm going to get the current data from the shadow. I'm going to load the shadow. Then I'm going to say, well, if I should update the shadow, which means that I'm getting these messages in the right order, and I don't want to clobber things. I'm not going to go into the logic there. I'm going to create a new shadow, and then I'm going to try and update the shadow. And this is a conditional update, where I'm going to say, update the shadow only if the new version is one more than the old version. So only if I'm moving the version just one forward at a time. And you can see that if two Lambda functions are concurrently running trying to implement this logic, they're both going to load their shadows. They're both going to decide, oh yeah, I need to update. One of them is going to win the race and update in place. The next one is going to lose that race. And at the moment it loses that race, update shadow is going to fail. So instead of it clobbering the update of the first Lambda, it's going to notice that it's about to do the wrong thing, and it's going to start this loop again. And it's going to get the current record data, and it's going to apply the business logic again, and so on. So in this way, we deal with all of these concurrency situations. And it's a very simple, powerful pattern for dealing with those issues. And we can do that because the local shadows on the Greengrass have these strong semantics around updates. And then, as another best practice here, in this loop, I'm going to sleep with jitter. So I'm going to sleep for a random amount. And the reason I'm going to do that is if I slept for a fixed amount, and I got, say, 10 messages at the same time, I would get one of them win the race and 9 lose the race, and then all those 9 would start again at the next moment, and one of them would win the race and 8 would lose the race. So we'd have this really kind of long linear thing where I'm kind of doing way too many tries. So the nice thing about doing a little bit of jitter here is on the second round, these things are going to be spread out in time and be much less likely to clash. So this is a decorrelation in time, and it's another good best practice when retrying things in the face of concurrency. And then I'm going to use the other capability of Greengrass, which is messaging, to publish an MQTT message to the cloud. And here again, I'm going to use that shadow to say, okay, well, when last did I publish to the cloud? And here again, I need to handle the concurrency case where there are multiple lambdas trying to do this. So I'm going to say, I'm going to try and update a shadow to say, I'm going to post now, and I'm going to do that again with this version check. And again, I'm going to go back to the beginning of the loop if my version check fails, so I can handle the case where there are concurrently executing functions. So what this code does is it loads that data from that shadow. It says, should I publish this? Which is the application of business logic saying, well, has it been a minute since I last published this piece of data? If it has been, then I'm going to try and update the shadow with the version check. And if that works, then I'm going to use the built-in SDK to do an MQTT publish. And that MQTT publish is going to happen locally. I'm going to publish that message to the Greengrass core software, and the Greengrass core software is going to forward it up to the cloud for me. And the nice thing about that is I don't have to deal with the failures of talking to the cloud here in my code. Greengrass core is going to deal with the cases of intermittent connectivity for me. It's going to deal with retries. It's going to deal with all of the realities, all of the ugly realities of the real world for me, and I don't have to worry about that in my code here. And once again, I'm going to do this kind of decorrelated sleep to spread my functions out in time. And then I don't have code for this, but I also want to say that for all of these pieces of business logic, you can configure them using a shadow sync to the cloud. And that's cool because it lets you use the synchronized shadows where you can change the values on the cloud side, and Greengrass core will synchronize that shadow down to the cloud for you, down to the device for you in the background, and again dealing with all of these messy realities of the real world. Which can allow you to say, well, it's winter, so I'm going to set my thresholds at a different place. Or this alarm's been super noisy and I don't think there's a real problem, so I'm going to increase my thresholds. And what a lot of customers are very excited about here is using this mechanism to pass down things like machine learning models. Where you're going to do the training up in the cloud and then inference locally and passing down the model parameters in a shadow. So let's talk about some highlights of the Greengrass API. So there's the Shadow API, which allows communications with devices. So this is this kind of traditional IoT or AWS IoT use of device shadows. Communication with AWS IoT, and this is the sync to cloud shadows. That's this configuration pattern, or the other patterns that you can use for synchronizing to the cloud. Or you can use it as a small local kind of quote-unquote database, this little document that is always there for you and has these strong semantics. It has these conditional rights and these other things that allow you to rely on that to implement things that deal with concurrency. Or just even in a simpler way, just stash some state. Then it's also got this messaging API, which allows communication with devices. Send that device a message, and today that's MQTT. And then communication with AWS IoT. Send a message up to the cloud. Or as Brett showed in his talk, part of John Turo's talk today, send a message to another Greengrass core, either directly or via the cloud. And that lets you build up architectures across multiple Greengrass cores. And that can be extremely powerful. So what's the same between Greengrass and the cloud? The same Python 2.7 support, the same event-based programming model. So all of those things, like that performance tip I shared earlier, that's going to work the same on Greengrass as it does in the cloud. So you can reason about things in a single way. And that was one of our goals as we designed Greengrass, to make sure that things worked as similarly as possible. And the container lifecycle and the programming model in general is a single programming model. And then what's different? And it's worth talking about why some things are different. And part of the reason that why some things are different is that the physics are different. These are smaller devices. The protocols they support are the protocols that are interesting in IoT and the protocols that are interesting in the cloud might not be the same. Managing a deployment of a Lambda function in the cloud and managing a deployment across thousands, hundreds of thousands, or millions of IoT devices have very different realities. So Greengrass is a very different IoT-centric or device-centric deployment and operational tooling system and monitoring and so on. So those are different because the realities are different. Instead of having a Lambda installation in one place in the cloud, in one AWS region, you could be running Greengrass on millions of devices. The authentication and authorization mechanisms are designed for devices, so they're designed to be lightweight. We think that security is extremely important, so we use strong authentication and authorization, confidentiality everywhere in this architecture. That's entirely handled for you by Greengrass, but the details of the way those work are going to be different locally than up in the cloud. And here we're using a lot of certificate-based and CA-based security, and we'll have documentation that goes into great detail on that. And then on devices, again, because devices are different, we're going to support both ARM and x86 with Greengrass. So ARM, typically a device like a Raspberry Pi, and x86 that could be Intel Atom or a server or whatever else. So thank you very much. I hope that was some useful information and a useful deep dive into the internals of Greengrass. If you have any questions, please go ahead and step up to the mic.